All right, so up to week 3 for theory lectures. Talked about resistors and capacitors, RC circuits last week. This week, going to get into inductors, RL circuits, as well as some transformers and diodes. So 3 basic components of electrical circuit have resistors, capacitors, and now inductors. Basically, it's like a coil of wire, and so as current goes through any wire, it's going to produce a magnetic field around it, kind of right-hand rule, so whichever way the current's going, this magnetic field circling around the current. If you have a coil of wires like we have here, you have this magnetic field that flows through the middle and loops around the outside. So these coils of wire are generally called inductors. And the way this works, using electromagnetics, Faraday's law, the electromotive force, also the same thing as voltage, is equal to the change in the magnetic flux as a function of time, or your magnetic field through a area dA. Generally, what you would have is an n number of loops through that change in magnetic flux gives you the voltage or EMF. So it's this rate of change in magnetic flux, which, as I said, the magnetic field depends on the current. So as the current changes, the magnetic field is going to change, and it's that change that's the important thing. So anytime the current changes, that's when inductors do stuff. If the current is the same, it's been the same for a really long time, inductors don't really do anything. So inductors are kind of like grumpy old men. You know, they don't want anything to change. They want everything to be the way it was 10, 20 years ago. EMF or inductors kind of work the same way, but instead of 20 years ago, it's more like 20 milliseconds ago. So if you change the current, the inductor doesn't like that, and what it does is it acts to counteract that. So if you increase your current, you're increasing the magnetic field, you're essentially increasing the voltage. The inductor doesn't like that, so it provides some back EMF. It basically provides some negative voltage to counteract that because it doesn't like what you're doing, doesn't like you changing things. Similarly, if you decrease the current, you're like decreasing the voltage. Again, it doesn't like that, it wants things to stay the same. So it's going to get some forward EMF, it's going to provide some positive voltage to counteract that and kind of try to make everything the same as it was before. So anytime you have an inductor, energy is stored in that magnetic field. If you change the magnetic field strength, you're either doing work or taking work out. If you're not changing the magnetic field of the current, then there's no work going on. And so the stored energy can be transferred back to the circuit. And so that's how that back EMF happens. You have a lot of current going in, so it kind of stores up that energy. And then when the current stops, it can push that energy back out to provide that positive voltage that was there before, but now it has to provide to make everything the same. There's an analogy for water. So if you have some tank, which is like a battery, some elevation to give it its potential energy. As you switch back and forth when the battery is on, that's kind of like this tank being on. And so water can flow through here, can go through the turbine. Turbine spins around and it can provide some energy to some outside source. If you then switch that off, this thing's already spinning around. And because this thing's already spinning around, it can push the water basically back up into the tank. So you kind of recharge your battery. So there's your back voltage. That's actually your forward voltage coming in to replace what the battery was doing. So you essentially shut the battery off. The inductor doesn't like that, so it provides its own voltage source to compensate for that and sort of try to make everything the same. Obviously, you can't do that forever because it's going to eventually run out of energy, but it does this in kind of this decreasing exponential form like you see here. We'll go through the math a little bit later, but very similar to capacitors, where capacitors can store up energy and release it later. Same thing for your inductor. Inductors are classified by their inductance, just like capacitors have a capacitance. Inductance basically tells you how strong the inductor is. Inductance L is measured in henries. So 1 henry will induce 1 volt of voltage if the current changes at 1 amp per second. So again, it's that change in current that matters. And just like capacitors, usually 1 henry is really big. You don't see them that big. In lab settings, you see microhenries to millihenries. And so this inductance, L, again, the measure of how much voltage can be produced when the current changes in time. So there's your coefficient of proportionality between the voltage and the change in current. You see here that if I changes really slowly, the induced voltage is going to be fairly small. So in that situation, if my current's not changing very fast, this number is really small. Again, things that don't change very fast, you don't really notice. And so the inductor is not really noticing that things are changing, and so it doesn't really do anything about it. On the other hand, if I change really fast, VL is really large, so it's going to do something right away to counteract that. Inductor symbol is kind of this curly, loopy thing, so it kind of looks like an actual inductor. So now if you look at the current and voltage through an inductor, so just easiest case possible, have some alternating current source, some inductor, so just those two components for now. Voltage coming out of the source, some peak voltage Vp times sine of omega t. Then from the definition of my capacitance, I can basically integrate that in time. So my current is 1 over L times the integral of the voltage through the inductor. Voltage through the inductor has to be the same as the voltage coming out of my source, because that's Kirchhoff's voltage law. It's only two things happening. So voltages have to be the same. So this VL voltage is just Vp sine omega t. Integrate that, you get cosine, and omega comes out. You have L on the bottom. So if you plot that, you'll see that cosine is shifted from sine. It's actually negative cosine, shifted from sine 90 degrees. It can be seen that the current is lagging the voltage by 90 degrees. So again, same voltage in both of them, but the current here is lagging. So what looks like ahead because of this time graph. So anything to the right in time is actually happening later, so it's lagging in real time. So here's my current behind my voltage, 90 degrees. Opposite of the capacitor was ahead by 90 degrees. So as I mentioned, energy is held in the magnetic field for an inductor. You can find the power the same way, so current times voltage, same thing as change in energy over change in time, which you can integrate to get the energy, integrate the power, expected time, get 1/2 Li squared. Very similar to the equation for the capacitor, so 1/2 CV squared. Now a little more complicated circuit, RL circuit, so RL series circuit to be specific. We have a resistor and an inductor in series. If you look at the current going through the resistor, we have some voltage of the battery, and then that voltage of the battery is split between the resistor and the inductor. So those two voltages, voltage over the resistor, VR, and voltage over the inductor, VL, have to add up to this VB. So VR is just VB minus VL. And then the current through that, by Ohm's law, just divide by the resistance. So that's the current going through the resistor. Current going through the inductor, same equation we had on the previous slide, related to the voltage through the inductor and the inductance. And then Kirchhoff's laws, add them all up, we get this differential equation, just like we did for capacitors. Obviously slightly different, but same sort of form. And then with this, we can define a time constant, again, similarly. Previous one was R times C. In this case, it's L divided by R, and that's going to act much the same way as it did for capacitors. And again, we have two cases. We have the charging case and the discharging case, depending on whether the switch is open or closed at time equals 0. So we can solve this equation based on the initial conditions. is this switch open, then we close it, and then see what happens, or is the switch closed, then we open it and see what happens. And so those will be the charging and discharging phases, just like we had for the capacitor. When it's closed, the battery is charging the inductor. When it's open, the inductor is discharging through this load voltage VL. So charging case, switch closed. So its switch was open and that t=0 switch is closed and stays closed for positive time. Solve that previous equation. If you have a constant applied voltage, so DC battery source essentially, we find that the current is VB over R, 1 minus exponential negative time over the time constant tau. So again, very similar to capacitors. Voltage through the inductor, VB e to the negative t over tau. So we can see the current kind of increases slowly. If the inductor wasn't there, the current would just jump up to VB over R and then go straight across. Again, this inductor doesn't like that. It doesn't like current changing that fast. So what it does is, even though the battery is providing this voltage, that should jump it up to here, the inductor is providing some back EMF, and so the current can only change this fast. And eventually it gets there, but it takes some time. Similarly, the voltage across the inductor, again, this is the back EMF. So this, right at time equals 0, it produces almost exactly the same voltage as the battery voltage, so that the current doesn't initially jump straight up. The current only jumps up by a little bit, and then again, as time goes on, jumps a little bit more, a little bit more, a little bit more. The back voltage that the inductor is providing drops down more and more and more as well, because there's less and less change in the current as time goes on. So biggest derivative, biggest slope at the beginning, so biggest voltage at the beginning, then drops away. Discharging case is a little interesting compared to what happened for capacitors. Nothing big happened for capacitors. Problem with inductors is that if you just open the switch, you've essentially changed the voltage that's being applied from some value VB to 0 instantaneously, which obviously in real life is not going to happen, but theoretically we can do that instantaneously. If you do it instantaneously, dt, change in time, is effectively 0. And so your voltage through your inductor is effectively infinite. So that is a danger in having an actual physical switch that you open and close with an inductor, because even if your time is not 0, it still can be very small. And if it's very small, you're still going to get a very large voltage out of this. And if you get a very large voltage while you're holding onto a switch, it's generally not good things are going to happen. So a couple options to suppress the spark. You can install a capacitor so that when the inductor discharges, it doesn't drop right down to 0, because the capacitor is here to help it limit that inrush of current. You can also place an RC series across the switch. So over here, you can have some capacitors instead of down there. Either way, that suppresses that instantaneous jump, and that way you don't have a infinite voltage, theoretically anyway. So assuming you avoid that very specific time equals 0, right after that, and assuming you did it safely, we end up with the same differential equation as before. Solution to this essentially the same as what we had for the capacitor. Current is VB over R, e to the negative t over tau. So again, discharging current drops down exponentially, very similarly. So I basically always talk about ideal inductors. So everything we've dealt with before is an ideal inductor. A real inductor is going to have some resistance, mainly because it's built out of wire, and wire, even though it's made out of copper that have very low resistivity, there's still something there. So there's still at least a little bit of resistance in the wire, and especially if you have a really big number of turns, because you have a lot of wire there, that's a lot of length. So you can actually get a decent amount of resistance out of a real inductor. So real inductor, you should have some internal resistance like we have here in series with your actual inductor. So every inductor is, in a sense, an RL circuit. If you want to get even fancier, you can have some capacitances around as well. So a more accurate model has some distributed capacitance around each winding, and the magnetic core losses, so another resistance based on those. And you can see, again, if you have a real inductor, you can't just jump in voltage. You get this curve, exponential curve like we saw before. So inductance, function of coil geometry. So is it circular, or how big is the circle? Things of that nature. So you can see these actually go around in a circle, even with windings in that circular form as well, kind of making a donut shape. This is just cylindrical with windings around it. The number of turns obviously is going to change things. Also the material, what's it made out of, and also what's the inside made out of. So you can see some of these. This one looks hollow, so there's nothing in the middle of that one. The other ones actually do have stuff in the middle of them. And so that all changes what the inductance is going to be. So in terms of the core, it deals with what's the magnetic permeability of the interior substance. So is it air, or is it something else with a much higher magnetic permeability? Commonly, you have things like air, so nothing inside there, or things like ferrite, iron, or from alloys, so more magnetic objects. You can actually calculate the inductance, so the value of L, based on all these geometrical factors. There's a few different equations based on this scenario. So I'll just point you to where those are in the textbook. So if you actually want to calculate the inductance based on all these geometrical factors and types of material and things of that nature, there's some formulas there. So generally, if you have a core with a high magnetic permeability, you're going to increase that magnetic field. And so that's going to increase that inductance. So that's why a lot of these are filled with magnetic materials, because it increases the inductance fairly easily, easier than having a lot more windings of wire. So that's a common thing to do. However, there are problems with these magnetic cores. One thing is that currents are induced in the core by these changing magnetic fields. Those currents feel electrical resistance, and therefore they dissipate heat, and that reduces the effectiveness of the inductor. Shorter current paths lead to smaller eddy currents, so we'll see this next slide here. There's some eddy currents. If you laminate with some non-conducting material, those eddy currents get smaller. And that's a good thing, because you have smaller losses that way. Iron cores aren't that great, because they exhibit hysteresis and saturation magnetic permeability. So those are not as common as other better cores like this guy. So iron core isn't that great, produces large eddy currents. Whereas this laminated one, some non-conducting material, ends up better. Now we saw that RC circuits can be used as filters, so filtering out different frequencies. Same thing happens for our L circuits. We can use those as frequency filters as well. So in the capacitor case, a low-pass filter involved taking the output voltage over the capacitor. For a RL circuit, involves taking the output voltage over the resistor. So this is a low-pass filter. It will let through any low frequencies. It will filter out any high frequencies. Similarly, the high-pass filter is opposite. So V out is taken over the inductor. That will let through any high frequencies. It will filter out any low frequencies. And the way that's done is, again, very similar to what we saw for the capacitors. We have some input voltage, which is some amplitude times a sine wave, assuming it's sinusoidal. We have some output voltage that's also sinusoidal with some phase shift, depending on the values of R and L. For the low-pass filter, the output voltage compared to the input voltage amplitudes is scaled by this factor, the square root of 1 plus omega tau squared. So again, same factor we had for the RC circuit. Only difference is that the time constant tau is defined differently because there's an inductor instead of capacitor. So L over R instead of R times C. And same thing for the phase shift. High pass filter, again, same magnification of the amplitude, omega tau over that square root, and same phase shift. So again, analogous to the RC filters, but LR filter is what's called turned around. In other words, the low pass filter here is over the resistor, whereas in the RC case, it's over the capacitor, and again, vice versa for the high pass filter. We saw last week there was capacitive reactance, so an impedance that was caused by the capacitor. Inductors also have a reactance, an impedance that they provide to the circuit, and that's obviously inductive reactance. And that's influenced by the current. That should not say capacitance, that should say inductance. And so like magic, it just fixed. Now it says inductance. So again, this acts as an impedance. In this case, it's 2 pi times frequency times inductance, or omega times L. So again, this has units of ohms, but no energy is dissipated. So very similar to the capacitor case. For high values of this inductive reactance, inductor acts like an open circuit. There's infinite impediment, so infinite resistance essentially. For low values, inductor acts like a short circuit, like it's not even there. There's no resistance in that case. So that was all about inductors. Next up is transformers. Transformers are kind of like 2 big inductors. So you have one inductor on one side, bunch of windings, another inductor on the other side, again, a bunch of windings. That's why their symbol kind of looks like this. You have the 2 inductor symbols essentially, and then some lines between them to indicate that they're actually working together in a sense, or coupled. So what happens is any sort of varying current is going to cause a changing magnetic field. So a varying magnetic flux in this core, that magnetic flux then comes over to the other side and induces a current in the what's called the secondary. So again, any changing current gives me a magnetic field. Those magnetic fields can also influence currents. So that's essentially what's happening here. So using the same basic laws as inductors, the voltage is related to the change in magnetic field over change in time. Also have some number of windings in there. If the primary and secondary are what's called perfectly coupled and share 100% of the same magnetic flux density, then the voltage is perfectly related to the number of turns. So voltage in the primary over voltage in the secondary is the number of turns on the primary divided by the number of turns on the secondary. If the transformer is also ideal, so ideal means there's no energy lost. If there's no energy lost, then the power in the primary, which is IPVP, is the same as the power in the secondary, no energy loss, which is ISVS. And I can relate this back to my number of turns. So number of turns in the primary times the current in the primary equals the number of turns in the secondary times the current in the secondary. So transformers can either be step up, where the voltage increases, so the voltage in the secondary is higher than the voltage in the primary, or step down, where the voltage decreases. So the voltage in this case in the secondary is lower than the voltage in the primary. So for a step-up transformer, I need the voltage to be bigger in the secondary than the primary. That requires more windings in the secondary than the primary. So a primary on the left-hand side has less windings than the secondary on the right-hand side. So the voltage again, I had to magically change these. For a step-up transformer, the voltage is larger in the secondary, so your output voltage is larger. So my output voltage larger than the input voltage, so basically just scaled. There's no phase shift involved, it's just scaled by this ratio of turns. So if I have twice as many coils on the secondary, my voltage will be twice as high. Step-down transformer is the opposite. Less turns on the secondary than the primary, so less voltage. So again, primary has a lot of turns, secondary has not as many. My output voltage is lower than the input voltage. It's kind of like gears. So however many windings we have is how many teeth there are. So a little number spinning around is going to spin this gear slower. And this analogy kind of goes with current. So if you notice in the step up and step down, that refers to voltage. If you look at the relationship, it's actually the opposite for current. So the only way to save power is if voltage goes up, current has to go down. So step up transformer, the voltage goes up, but the current actually goes down. Step down transformer, voltage goes down, but the current goes up by that same factor. So that's what this gear analogy is for. It's basically looking at speed as current. So small number of windings, small number of teeth is going to spin this angular velocity much slower on the secondary. Again, that's like your current. Same thing if it's reversed. So step down transformer is going to spin this gear really fast, higher current. And the voltages can relate to torques. So the transformer is unloaded. AC voltage applied to the primary. It's just like a normal inductor, so nothing's happening over here because this is unloaded, there's nothing to do. So there's going to be nothing induced on the secondary side. And we'll just have essentially this left-hand side, just like we saw 10-15 minutes ago when we dealt with just an AC source and inductor, the current lagging the voltage. For the loaded case, that's again what you're generally going to have. So there's hardly any time there's nothing over here. Usually there's at least a resistor. That's the easiest case anyway. So having just a resistor, have some voltage going through it, that's the same as the voltage in the secondary. And this load actually determines the current on both sides because there's no resistor on this side to determine this current IP. It's really this resistor that determines current IS. IS then determines IP through the winding ratio. So I have some voltage in the primary, which is some peak voltage, Vp0 times sine omega t. Then voltage in the secondary is again some peak value, sine omega t. And this peak value I can get by relating the voltage and windings. So now that I know V as 0, I can divide that by R to get the current. So my current, again, is a function of time, sinusoidal function of time. Then by the transformer current rule, current in the primary times turns in the primary is equal to the same thing on the secondary side, so I can solve that for IP. And then kind of put these things together. So IP amplitude is NS over NP times IS amplitude. And then IS, amplitude, is Vs over R. And then Vs is Ns over Np times Vp. And so what I end up with is Ns squared over Np squared times Vp over R. So essentially my, on the primary side, I have the resistance on the secondary side times this factor of Np over Ns whole thing squared. I can call that R effective. And so my effective resistance on the primary side is related to the resistance on the secondary side through this, again, winding ratio, but now squared. And RF is my effective load on the primary. Again, it's completely determined by the number of turns, the transformer itself, as well as whatever my load is, so the load resistance. So we look at the power through a transformer. The voltage in the resistor is the voltage in the secondary, which is VSO sine omega t. The current in the resistor is the voltage divided by the resistance. And so the power dissipated is V squared over R times sine squared over omega t. You can see that this is actually oscillatory in time, and actually at twice the input frequency. There's a trig identity. Sine squared is the same as cosine of 2. So twice the frequency is what happens with the power. So how this works, again, secondary sets up the magnetic field, produces the primary field. So they induce voltage to equal the primary voltage. You need to have the original field be maintained. Primary draws enough current to make that field equal and opposite of the secondary, which means, bottom line, is that these are actually out of phase by 180 degrees. So the voltage in the secondary is actually 180 degrees out of phase with the voltage in the primary. That's the takeaway from this. Again, real transformers, we're looking at the ideal case, so just inductors. We don't know that inductors actually have some resistance as well. So there's, in addition to the inductors, there's resistances. So the winding resistance, again, that's the resistance to the actual wires. There's some leakage reactance provided by the capacitors, not the capacitors, the inductors as well. That's kind of non-ideal magnetic fields going different places, and also some distributed capacitance, which we kind of talked about as well. So real transformers do actually have energy loss. We're not going to worry too much about that in this course, but in real life, the power is not exactly the same. So your power in the secondary is not the same as the power in the primary, so you don't have ideal transformers. Another variation that we might see is a center tapped transformer. So in other words, you have the tap down the middle. So you almost like you have two different windings on the secondary side. So you have secondary winding number 1 and secondary winding number 2. So you have two different voltage sources essentially. And again, these depend on essentially the number of windings. So you still have a winding ratio. So however many windings I have in VS1 compared to VP tells me what that voltage is. And then the same thing independently for VS2, however many windings I have compared to VP tells me what the voltage is in that one. Interesting thing about this is that my secondary voltages are 180 degrees out of phase with each other. There's many other varieties. That's kind of the most common one. There's also these where you have all sorts of different taps going on. So those are transformers. Last thing to deal with today are diodes. So diode is a semiconductor device. We'll talk a lot more about semiconductors next week. But a diode allows current to flow in only one direction. That's ideally, of course. That's going to flow when the current in the anode is higher than the potential in the cathode. So it's going to go from anode to cathode. So this is your most common symbol for the diode, kind of pointing in what direction the current is allowed to go. So if you stick this on the positive side, that on the minus side, current will be able to flow through there. if you stick it in backwards, current will not be able to flow. And that's the same thing you kind of ran into with LEDs. LED is a light emitting diode, so it is one of these devices. If you put it in backwards, it will not allow current to flow. If you put it in the right way, it will allow current to flow and emit light, as its name suggests, as it's doing so. Diodes are usually made out of silicon or germanium. Again, next week we'll talk about all the gory details of semiconductors. Right now, it's going to deal with a few uses of them. We've already used a few of them. As I said, you've already used LEDs, but we'll be using more of them this week and later. So 6 things you need to look at when in terms of diodes. So there's a junction threshold voltage. So it takes a certain amount of voltage to actually, for the diode to actually start letting current through. And that's called your junction threshold voltage, also called other things that we'll see later. So different types of diodes have different threshold voltages. So in terms of current on the y-axis, so nothing really happens until I hit this value of the threshold voltage, and then it lets pretty much all the current through fairly quickly. There's a peak inverse voltage. So eventually, if you put this in backwards and load it up with enough voltage, it will eventually start letting stuff through, even backwards. But that's generally not what you want to have happen. Maximum forward current, I0 max. So again, if you have too much voltage going forwards or backwards, bad things start to happen. There's a time response, so how fast that actually all happens. There's some leakage current. So again, if you do it backwards, it doesn't let much current through. So ideally, a diode will let 0 current through if it's put in backwards, but in real life, it lets a little bit through, but just not very much. And so that's your leakage current. And then there's a maximum forward voltage drop. So if you put too much voltage in processing, bad things happen, as indicated in this figure. Diode equation given by current is my leakage current, I R max, and then forward voltage over something called a thermal voltage, e to that whole thing minus 1. Thermal voltage is given by this equation, Boltzmann's constant times temperature over the charge of an electron, so 1.6 times 10 to the negative 19 coulombs. For 300 degrees Kelvin, you're looking at roughly 0.026 volts. And so your current is going to increase by a factor of 2.7-ish for each 0.026 volts increase in the voltage. So you can see that the current increases very, very fast. So again, for an ideal diode, lets through 0 current until you hit your threshold voltage. And as soon as you hit your threshold voltage, it jumps up to whatever the current is supposed to be in the rest of the circuit. You see, for this reason, we've always had you put a resistor in series with a diode. So you want that resistor there to cut off this current at a reasonable number. If you don't have a resistor there, this current will jump up to a very, very high value and probably melt your diode. So essentially, a diode acts like a short circuit if the voltage is bigger than the threshold voltage. I'm just going to call it 0.6 from now on. That's the typical value for silicon, I think. Yeah, silicon. So really, this should be V threshold, but I'm going to call it 0.6. Acts like an open circuit if V is less than 0.6. So if you have less voltage than that, nothing's going to get through. Again, for the ideal case. So again, these numbers, I've called it 0.6, but can really be any of these. So germanium as low as 0.2. Silicon is where I got that number from. Generally, they're somewhere between 0.2 and 1.7. LEDs are usually in the higher range. Usually when we deal with diodes, you have a really high voltage source. So if you have something coming out of the wall, for example, you're looking at 120 volts. if I have 120 volts, I'm not worried too much about 0.6 volts for the LED. So a lot of times you ignore it. So this threshold voltage, also called the turn-on voltage, as I mentioned, has a few names. So that's another name for it. Generally, if it's less than 20 volts, you might want to take it into account. So looking at labs, generally in our labs, we're dealing with like 5 volts coming out of the Arduino. So compared to 5 volts, this 0.6 volts is relatively important. So diode, generally you think of it as a switch. So it's kind of like a switch dependent on which way things are going. So you can kind of set it up in your circuit where if you want things to go a certain way, you put a diode there and that will force things to go that certain way. Anything trying to go the other way is going to get stopped. So nothing will move the other way. The nice thing about this is that you can use this as what's called a rectifier. So rectifier is kind of like a negative voltage filter. So if I have a negative voltage, that's going to set up a negative current. Negative current means it's going in the opposite direction. So for example, if I have a AC waveform where things go positive and negative, I have some threshold voltage, and call it 0.6 volts. So I'm just going to say this line is 0.6 volts. And this line of 0.6 volts basically cuts off. Nothing down here is going to get through because it's lower than the 0.6 volts. So the only stuff that gets through is these positive parts of the waveform. So what you get out of it is just this positive, and basically nothing in between because the diode is taking that out in the circuit. So diodes are used a lot as rectifiers to do just what I just said. And so they're often called rectifiers because that's what they do. And so you see here a lot of different packages in terms of diodes and rectifiers. So many applications of diodes. In DC circuits, you can use them to reduce the voltage by certain increments. So if you want to reduce the voltage by 0.6 volts, and then go through some components, and then reduce the voltage again by 0.6 volts, go through some other components. You can do that by putting diodes in your circuit. So once I go through, I have 5 volts coming out of my Arduino, I then go through a diode. Whatever goes into the next component is only at 4.4 volts because the diode took up about 0.6 volts. And then if I go through another diode, I'm down to 3.2. Another diode down to 3.8. Another one brings me down to 3.2. So you see, as I go through each diode, my voltage gets reduced by that same amount. So that's one application. The other application, as I said, is this rectifier. So it essentially is very useful in turning an AC source into a DC source. So a lot of times you have AC source that you want to turn into a DC source. That happens a lot, especially with things like computers. You have your wall, anything that needs to be charged into the battery. Batteries are generally DC, but you charge them by plugging something into a wall, which is AC. And so what's inside your little charging device is basically some of these. So it's converting the AC source from the wall into a DC source to charge the battery. So the simplest one is called a half-wave rectifier. Half-wave rectifier essentially just stick a diode in your circuit. So I have my AC input through a transformer, so that can change the peak voltage. Diode essentially just cuts off all the negative part. So I have my AC input, V0, AC waveform, and then this just cuts it off at whatever the threshold voltage is. And then at that point, my maximum voltage is V0 minus this threshold voltage. So if I have 5 volts coming in, cut off from the diode, now my peak voltage is only 4.4, but it is all in the positive direction. There's no negative voltage left over. Now, what I had before is, voltage somewhat sinusoidal and then nothing, and somewhat sinusoidal then nothing. And that's not the greatest DC source. DC should be some constant value. So a way to fix that is to stick a smoothing capacitor in the circuit as well. So if I stick a capacitor in here, I now have an RC circuit. Remember RC circuits, my capacitors are going to charge and then discharge. So if I have that same waveform, it's still here. So here's in purple, I have my positive value, then nothing, then my positive value, then nothing. Adding this capacitor in here, this positive value is going to charge my capacitor. My capacitor is going to charge. And then as soon as that voltage starts to drop off, my capacitor is going to discharge. And if the value of the capacitor and the resistor are fairly large, I'm going to have a fairly large RC time constant. And so this is going to discharge fairly slowly. So as this is discharging, my actual voltage source goes down to 0 and then comes across and starts to charge again. And then eventually those two voltages meet and my capacitor charges again. And then again, discharges, charges, discharges. This is called a ripple. So my voltage is kind of alternating. It's not going alternating from +5 to -5, but it's alternating maybe between 5 and 4. So it goes up to 5, drops down to 4, up to 5, drops down to 4. And obviously you want to make that ripple fairly small for DC sources, so make fairly large values of resistors and capacitors, and that will reduce, that's one way to reduce some of the ripple. So that's called a, or both of those are called half-wave rectifiers. Half-wave because it's essentially, once you've rectified it, you only have half of the input. So once I've cut this off, all the negative part's gone. I'm only left with half of the wave, which is not ideal. So more than half of the circuit, I'm not getting any voltage out of it. So that's not great. Better ways are called full wave rectifiers. So there's a couple ways to do this. First one is a center tap full wave rectifier. So you take a center tap transformer, and then anytime the waveform is positive, it is allowed to go through this diode. Anytime the waveform is negative, it's allowed to go through that diode. So remember that for the center tap transformer, the two sides of the coil were out of phase by 180 degrees. So if that's the case, then whatever is positive down here will be negative up there and vice versa. So at every situation, we'll have at least half a wave coming through. So the input on the secondary side is now like this. So you don't have those negative parts anymore because this diode is kind of taking care of it, but you still have that threshold voltage being cut off. But you end up with a lot more parts where you're actually getting power as opposed to sitting off in zero land for half a wave. You have, so this is called a full wave rectifier because you actually get power almost the entire time. Downside of this is that you're not using as much power out of the transformer. So the fact that you have to cut this in half means your windings have both essentially been cut in half. So because they've both been cut in half, so again, only half of it's actually being used at a time. So nice thing about this one is I only have one diode per voltage drop, so 2 diodes total. Bad thing about this one is low power utilization. The other option for a full wave rectifier is called a full wave bridge rectifier. So this one, as you can see, has 4 diodes. This is a type of circuit you'll be building in lab this week. And so in this case, same sort of deal. You have the same sort of waveform come out. You still have you still have all positive sides. So still a full wave bridge rectifier. Has good power utilization because it's there's no center tap, so you're using the entire voltage source each time. But you have 2 voltage drops per side, so anywhere you go through, you're either going through D4 and D1, or you're going through D2 and D3. So you have to go through 2 diodes, which means you go through 2 voltage drops, and 2 voltage drops is twice the reduction. So if you're dealing with a small voltage source, only like 1 or 2 volts, you have to drop down 0.6 volts to 2 of them. That's obviously not a good thing to do. If you're dealing with a high voltage source, then this is not an issue. So not popular for low voltage applications for obvious reasons. So here is positive cycle, you're going through D1 and D2, negative cycle going through D3 and D4. So here is your waveform again, full wave rectifier. So you have not any case where we have 0. And then again, capacitor charges, so it charges up, and then discharges, charges up, discharges, charges up, discharges. Have a little bit of a ripple, have this DC, average DC voltage come through there, which is pretty close to the peak voltage, which is nice. Peak voltage been reduced by 2 diode voltage drops, or threshold voltages. So adding a smoothing capacitor obviously gives you this little ripple up here. If you didn't add the smoothing capacitor, you just have this purple line output waveform. So those are basics of inductors, diodes, transformers, and rectifiers. Hopefully you have fun this week in lab building circuits like this.